We'll continue with our review of graphs of trigonometric functions. And we will start by solving this problem, number 35, from page 594. And after that, we'll do number 13 from page 592. Both of these problems from Sullivan textbook. So this problem 35 is about modeling data, hours of daylight. So let's read it together here. It says, according to the old farmer's almanac in Miami, Florida, the number of hours of sunlight on the summer solstice of 2010 was 13.75. And the number of hours of sunlight on the winter solstice was 10.55. So the first question is to find a sinusoidal function of this general form, y equals a times sine of omega x minus phi plus b, that models the data. For part B, we have to use the function that we found in part A to predict the number of hours of sunlight on April 1st, the 91st day of the year. C would be to draw a graph of the function found in part A, and D, we should use the old farmer's almanac to find the number of hours of sunlight for April 1st, and then compare the actual hours of daylight to our results found in part C. So I'm gonna switch now to my whiteboard, and we'll proceed with all these calculations. As you see here, only two sets of data are given. So we just know only the number of sunlight at summer solstice is 13.75, and then the number of hours at winter solstice, both of this in Miami, Florida, right, is 10.55. So I'm gonna switch now to my whiteboard. Okay, move this here. Okay, so let's see. So we are looking for a sinusoidal function in the general form of a y equals a times sine of omega x minus phi plus b, or usually we put this form, we just force factor the omega. So we'll have here this ratio phi over omega, which is the phase shift, plus b. Okay, so what do we know? We just know the number of hours of sunlight. I'm gonna make a table here, an x and a y. So remember, we know the number of hours of sunlight at summer solstice, which was 13.75. And then we also know the number of hours of sunlight at winter solstice, which was 10.55. So here, basically, y represents the number of hours of sunlight, and x represents the day number. Okay, so for the summer solstice, June the 20th, we'll take the day number, which is 171. And for the winter solstice, we have the number that's happening on December 21st. So that's the 355th day of the year. Okay, so as you can see, we know that the numbers of hours of daylight will happen periodically, but we want to find this function more specifically. So what do? It's interesting that we have only two sets of data, but actually with this and with some more, a little bit of science information, we will actually be able to find a function. So how do we do that? First of all, we can find the amplitude. And why? Because as you know, the amplitude will depend just on the maximum value and the lowest value of y, our function. And we know both of them. So the amplitude, as you know, is the highest value minus the lowest value, and all divided by 2. So our highest value is 13.75. The lowest value, the lowest number of hours of sunlight in 2010 is 10.55 in Miami, Florida. So that divided by 2, that would give us 3.20 divided by 2, which is 1.6. Okay, now we have the amplitude. With the highest value and the lowest value of our function, our trig function, we can also, actually I should say our sinusoidal function here, we can also find the vertical shift. So the vertical shift, which is actually b in right here in our sinusoidal function, is actually the average of the highest value and the lowest value. So it's going to be 13.75 plus 10.55, all divided by 2. If we add these numbers together, we get 24 plus, 24.30 divided by 2, so that's going to be 12.15. Okay, so so far we know A and we know B. Now, what else do we need? We need to know omega, and we also need to know this phase shift. We can find omega pretty easily because, as you know, omega is related to period. So period is 2 pi over omega. And period here would be 365, because every 365 days, this process will repeat. If we take this equation and we solve for omega, omega will be equal to 2 pi divided by 365. Okay, now we go back to our function here. We put everything that we know so far. So we have y equals A amplitude, which is 1.6, sine of parentheses omega 2 pi over 365. Then we have x minus this ratio here, which is the phase shift, and we don't know, we know what is omega, but we don't know phi, but actually we'll be able to find the whole ratio, the phase shift, in a moment here, plus b, the vertical shift, which we found to be 12.15. Okay, now, how do we find this phase shift? Well, let's think about this sinusoidal function that we have here. So we'll take just one full cycle, okay? So let's say we have this curve here, right? So if it's one full cycle, it should be extended over a period of time of 365 days, okay? So I take this 365 days and I'm going to divide it in 4. Why? Because I'm interested into this maximum here. So I'm going to divide it into 4 equal subintervals. So I'm going from here to here to here. So that's day 1. This is day 365. And I divide it into 4 subintervals. So you see I have 1, 2, 3, and 4. Okay? So 365 divided by 4 is actually equal to 91.91. 91.25 days. So basically this maximum here should happen after, on the 91.25 day, right? After 91.25 days. But according to our data, this is happening at day number 171. So there is a difference, right? There is a difference. Our graph is shifted to divide by a certain number of units or days. It's going to be 171 minus 91.25. And if we subtract this, we'll get 79.75 days. So our whole sinusoid is shifted to the right by 79.75 days. Again, how do we know? Because the maximum is happening at day number 171, which actually should happen at 91.25. So now we go back and we rewrite our sinusoidal function, which is this one. So we just say y equals 1.6 times sine of 2 pi over 365 multiplied by x minus, so now I have to put a phase shift, which I said is 79.75, and then I have to add 12.15. Okay, so that was question A. Now for question B, we have to find out the number of hours of sunlight on April 1st, 2010. And they tell us that that's day number 91, x equals 91. So I'm going to put 91 into my function here. 1.6 times sine of 2 pi over 365 multiplied by 91 minus 79.75, and then plus 12.15. And of course, I have to use a calculator to find this value, which I did, and I will show you in a moment. We can check it. I got 12.46 hours, about 12.46 hours. Okay. Now it says here, use the old Farmer's Almanac to compare with the value that they have there. And guess what? So I look there and it says that the number of hours of sunlight on April 1st, 2010 was 12 hours and 26 minutes, which converted just in hours is about 12.43 hours. So as you can see, we have a pretty good approximation, even though we used only just 2 set of points, okay? Just 2 points, okay? The summer solstice and the winter solstice. Okay, so now we also have to graph it. So I'm gonna switch now to my graphing calculator, and let's graph this function. Let's see how it looks like. Actually, before we graph it, let's look a little bit to make sure what do we use for the window for x and for y. So remember that x represents the number of days in a year. So we'll take x from 0 to 365. And then we need y, which is this sinusoid right here. And actually we can see, we can, again, we can look here, or actually we can look at our data. We can see that the lowest value that y has is 10.55. The highest is 13.75. I'm gonna leave a little bit of space above and below. So I'm gonna say I'm gonna go up to 15, let's say, and I can start at 0. Okay, so we are gonna have to use these values for our windows. So I'm gonna stop sharing my whiteboard now, and I will go to my calculator. Okay. Okay, so now I'm gonna share my screen, my desktop. Okay. And I'll go to my calculator. And I'm gonna just graph this function that we just found, 1.6 times sine of, let's see, what do we have here? We have 2 pi divided by 365. 365. And then multiply by the quantity of x minus 79.75. Okay. And then we have to add the vertical shift, which was 12.15. I also have to go back to my window here. And I have to make sure that I have those numbers that we were just talking about. So x will go with x from 0 to 365. And then for y, we said that we should go just from 0 up to 15. And now let's graph and let's see what we have here. Okay, pretty nice graph, right? So you can see that we have here a full cycle, and then here it starts repeating again. Okay, so that's it about this problem. Now we'll move on to number 13 from page 592, which is about graphing a sinusoidal function. So I'm gonna stop sharing this calculator, and I will go back to my whiteboard. Okay, so let's see. Can we move this larger, clear? Okay, so number 13 on page 592 says this. We have the function y equals -3 sine of -2x plus pi over 2. Remember that we prefer to do a force factoring here of the coefficient of x, which is -2 in this case. So if I force factor -2, I'll have x, and then I'll have minus pi over 4. Okay, now I'm going to write here the general form of a sinusoidal function, a times sine of omega times the quantity of x minus pi over omega plus b. And I'm going to use this just to find the main values here for this function. So step number 1 is to find the amplitude, the period, phase shift, vertical shift, if any. So let's start with the amplitude. The amplitude A is the absolute value of this number, -3. So that becomes 3. Then we'll find period, t equals 2 pi over absolute value of omega. In our case, it's 2 pi over absolute value of -2, so 2 pi over 2, so that becomes pi. Then we also look for the phase shift, and just by comparing these two, we can see that the phase shift is pi over 4 to the right. And then we look for a vertical shift b, but we see there is no b, so b is 0. So that was step number 1. For step number 2, we'll decide to graph just one full cycle. So we're gonna take the starting point of our full cycle here. So it would be this value pi over 4. Our graph was moved to pi over 4 to the right, so I'm gonna take pi over 4. And then I'm gonna take the ending point of this cycle. Remember that one full cycle is extended over one period, and period in this case is pi. So if I start with pi over 4, I add a pi, and I'm getting the ending point, which would be pi over 4. So now my first cycle here goes from pi over 4 to 5 pi over 4. Okay, so again, the distance from one point to the other is just pi. I'm going to take this and I'll divide it into 4 equal subintervals. So it's t divided by 4, which is pi divided by 4. So each subinterval will have a length of pi over 4. And I'm going to make a table of values here. I'm going to put x and y. And as I said, my starting point is pi over 4 for x. The ending point is 5 pi over 4. And I'm taking this interval and I will divide it into 4 equal subintervals. So right in the middle, between pi over 4 and 5 pi over 4, I just have to do the average. Pi over 4 plus 5 pi over 4 is 6 pi over 4, or reduced to 3 pi over 2. Divided by 2 is 3 pi over 4. Or you can just look just here. You have a 1, here you have a 5. Both of them have pi over 4, right? 1 plus 5 is 6, divided by 2 is 3. So it's 3 times pi over 4. Okay, now I will repeat the process to find the midpoint here and the midpoint here. So this one, pi over 4 plus 3 pi over 4 will give me 4 pi over 4, or pi divided by 2 is pi over 2. Here, you take these two values, add them up, divide by 2. So 3 pi over 4 plus 5 pi over 4 is 8 pi over 4, or 2 pi. Divided by 2 is just pi. Okay, now we're going to find the y values for each one. So let's start with pi over 4. We take the value back into the original function. So you just go up here, okay? We can even write it here, -2 times pi over 4 plus pi over 2. So let's see, what do we get? -2 times pi over 4, we cancel this. We have negative pi over 2 plus pi over 2, which is 0. So we have a sign of 0. Sign of 0, as you know, is 0. Multiplied by -3 is going to be 0. Now, y will become again 0 when x is 5 pi over 4, because as you know, this is a periodic function. So y will go back to the value of 0. A 3 pi over 4, we expect to get again a 0. So that's where we'll check right now. So let's take x equals 3 pi over 4 back into our original function. So we have -2 times 3 pi over 4 plus pi over 2. So you see this is canceling here. So I have, what do I have here? I have -3 pi over 2 plus pi over 2. That's going to be equal to -2 pi over 2, which is the same as negative pi. So now I have sine of negative pi. Sine of negative pi. If you remember, sine is odd, so that's negative sine of pi, which is actually 0. Multiplied by -3, again 0. So I have a 0. Now let's see what's happening at pi over 2 and at pi. Okay, so I take pi over 2 back into my function. So I have -2 times pi over 2 plus pi over 2. So basically this is -2 pi plus pi, all divided by 2, or negative pi over 2. So now I have sine of negative pi over 2. Sine of negative pi over 2, the same as negative sine of pi over 2. Okay, which would be -1. -1 times -3, that becomes 3. Now one more value here, pi. I would expect to get here -3. Because as you can see, your function is just the sine multiplied by -3. So you should go between -3 and 3. So I would expect here to get a -3 since I have no vertical shift. So I'm going to take pi into my original function. So I have -2 times pi plus pi over 2. Or that's the same as if I put this as a fraction, -4 pi plus pi all divided by 2, or -3 pi over 2. So now I have sine of -3 pi over 2. Okay, or I can say negative sine of 3 pi over 2. sine of 3 pi over 2 is -1, and with this extra negative, it will turn into a +1. But then when I multiply by -3 here, which I had originally, this becomes -3. So now we are going to graph. As I said, we'll do only one full cycle here. So our starting point is a pi over 4. The ending point is 5 pi over 4. So I'm going to just take, let's say I'm going to put here pi, and I'm going to take a 2 pi. Let me move this x here. Okay. So midpoint here is pi over 2. Then I have pi over 4. Then I have here 3 pi over 4. And then I have to go 1 extra pi over 4 here to divide, so that becomes 5 pi over 4. I also know that y goes just between -3 and 3. And I'm going to plug these points, these 5 key points on my coordinate system. So when x is pi over 4, y is 0. So I have a point right here. When x is pi over 2, y is 3. So the point will be up here. When x is 3 pi over 4, y is 0. When x is pi, y is -3. And when x is 5 pi over 4, y is 0. Okay, so now I have this beautiful full cycle of this function here. Okay, looks nice, right? Right here. Okay, now I'm gonna just switch to my graphing calculator just to check this graph with the one that the calculator will give me for this function. And I will also look, I will also put the parent function sine of x to see what kind of transformations are actually happening here. So right now I'm gonna just, I'm gonna switch back to my desktop. Okay. So share my screen, desktop. Okay, and I'm taking my calculator. So basically what happened? That's the function here. And what do we see here? Remember, we have here the screen, we can find it, which means that our graph is vertical. our functions in time. When it's in time, we need that we have a reflection over x very much to the graph. So you have this, as I said, you have stress, you have a reflection of an x. And so in that here, if you see x is multiplied by 2, but also we have a negative. And remember, we can also write this as negative 2 times x minus 5. We have a horizontal shift of 5 to the right. But we also have a horizontal compression. Again, that's the graph. It's an horizontal compression. And you see the step for the compressed horizontal. And the period basically was changed from 2 pi to 5. So the period was cutting half. Now, also what happened, we also have that the negative in front of the two, was which was actually a um, reflection over the wires. So all these transformations, and of course, in the order will make us go from the given function kind of x to this given function y equals negative 3 sine of negative 6. So that's it for today. So we'll stop here and we'll continue tomorrow.